Good morning, class.
Hello. Morning.
I'm on the mic because we're recording for no reason we yet understand. Okay, good. Just reminders. Those are the URLs. I don't know if you can read them, but this one, it says Flatiron CD8. It's dwh.gg Flatiron CD8. That is the syllabus for the course. If you are not on the email list, you should be on the email list. It also tells you how to get building access, but somehow you all manage that. So probably you have all seen this. And then there's another document, FCDA Notes, which is where some very, very enterprising people who I now owe beers to have been taking very nice notes. And I very much appreciate that. And if people want to continue taking notes, I'm very, very excited about that. You could even admit who you are on that document, and if we ever decided to write something up from one of these classes. There are some chairs at the back and on the side. Oh, and the front row. Front row. Okay, good. Let's just jump in. And as always, we're going to start with my favorite equation in all of data analysis, because we need to go back to the same equation to remind ourselves of where we're at. So you will, as we emphasize, I promise you that as of next class, we will not be writing this equation on the board anymore. I promise. So, of course, it will come back later in the semester. But in a linear model, you have an estimator for your parameters, which looks like M transpose C inverse M, all inverse, M transpose C inverse Y. And let me just remind you, I'm just reminding, this is the least squares estimator in a linear problem. This is your data, which you can think of as a column vector. This is the noise. This is the inverse variance for the noise on your data, which is technically a matrix, though you'd never constructed it that way. This thing is the design matrix. This thing is the design matrix. And this thing is the Fischer matrix. And that's what we talked about last time when we talked about information theory. That's the Fischer matrix. And when you invert it, it becomes the uncertainty on your parameters in the unbelievably unrealistic position that all of the assumptions you made are correct. And remember, we made a boatload of assumptions to get to this point. We assumed that the noise was known. We didn't assume that the data points were independent, actually, because once we write this as a covariance matrix, we're not assuming that the points are independent, but we assumed the noise was known. We assumed the noise was Gaussian with zero mean, no bias in the noise. We assumed that our model that we were using was a correct model, meaning the data really were generated by the linear fit described by this design matrix. And we assumed there's no intrinsic scatter, no outliers, blah, 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 blah. We assumed a ton of things, okay? Now, in any real situation, all of these things are not true. Maybe not in any. I know a few very rare situations in which you really can rely that your noise is Gaussian. I do know some cases, but almost nobody in this room is in any of those cases. It is certainly never the case that you know the noise variance. That you never do. And the reason there's really deep reasons you can't know that your noise variances. And that's because in order to assess your noise variances, you'd have to take fourth moments of your data, and you could never have, even all of LHC operating for all 20 years will not give you enough data to do fourth moments. I see a chair next to Alex. Good. Of course, your model's never correct. That's something we're going to discuss all through the semester. And in general, you know that that other things about your model are not right kind of intuitively. Like, for instance, you know that sometimes your system glitches or has problems, and you just have some weird points that have weird properties. Okay, good. So that means, and I want to say something, that this Fischer matrix, as we discussed, if all of these things are true, then this thing represents your uncertainties. This thing, inverted like this, becomes the covariance matrix on the parameters of your linear fit. There's two things I want to say about that. First of all, technically the Fischer information is involved in the Cramer-Rao bound. So this is the best you could possibly do. So for one, if all these are true, this is the best you could possibly do, and it is what you do. But then this is the other thing I want to say is this is very brittle in the sense that if any of these become not true, this will no longer be a correct assessment of your uncertainties. And the only principled way to figure out your uncertainties would be then to model exactly the ways in which these are not true. And that's something you don't have capacity to do in general. If you do, however, that's what you should do. But in this class, we're going to talk about the realistic situation that everybody finds himself in, where they don't really believe that all these things are true. Now what do we do about assessing our uncertainties? So this class is just about assessing uncertainties, and it's about using empirical, pragmatic, real-world techniques. And I wanted to emphasize, and I did in the little summary of today's lecture, that I want to emphasize that these methods are backed up by research. So these are not hacks. We sometimes think of them as hacks, but they're not hacks. There's a huge literature on Bootstrap, Jackknife, and cross-validation. That literature shows asymptotically correct properties of these methods. And so there is a set of assumptions under which Jackknife and Bootstrap is actually a completely valid way to determine your errors. Those assumptions are also hard to meet, but they're easier to meet than these. Okay, good. Questions? Yes?
Actually, so the Fischer matrix, especially the information that you discussed last week, after going away from this class, I was wondering, is there a more intuitive way to think about information rather than the curvature of the...
So Wolfgang is asking whether, we talked about last time as the information, he's asking, is there a more intuitive way to think about this than as the curvature of the log likelihood function?
Is that right? Yeah.
This thing is the second derivative of the log likelihood function.
Yeah.
That is how it got there.
Yeah.
It's funny that you say that because I think the only intuitive way to think about this is that it's the second derivative of the log likelihood function. So I got nothing for you. No, one thing that I like to emphasize, and I've been forgetting to emphasize, is dimensional analysis. So one thing that might help is that this has units of 1 over data squared, right? Because this is an inverse variance for the data. So this is units of 1 over data squared. And the design matrix is data per model parameter. This has units of data per model parameter. And this has units of data per model parameter. So the units of this thing end up, the data units cancel out, and you get per model parameter, and this is 1 over model parameters squared. So it has the right units to be the inverse variance of your model parameters. I don't know if that helps. Another thing, do you want to help with intuition?
Well, I just want to know, I have a way of thinking about it, and I want to know if it's
Fire it
a
up.
valid one.
Fire it up.
Can you think of it as like a Taylor expansion? So you go to the position of maximum likelihood, and you Taylor expand, and then the first derivative has to vanish, and then so you only get a second derivative?
It's Caitlin.
Yes.
Welcome. Caitlin asks, is it intuitive to think of this as the first term in a Taylor series? I am certain that it is. I'm certain that that's a good idea. Absolutely. In some sense, whenever you put just an error bar on something, you are talking about the first term, because of course you in fact have an uncertainty distribution that's very non-trivial. And And the width of a Gaussian is the second derivative of the log of the Gaussian. That's just numerically, that's how you get it, or the inverse width. But so in some sense, the fact that we can stop at the first term in the Taylor series is related to the fact that we can make these assumptions. If these assumptions stop holding, then all of a sudden we have to go further, and then this describing your uncertainties with a single number doesn't work. Actually, one really key thing is if you allow outliers, if you model your system with outliers, in general you don't even get a unimodal likelihood. You'll get multiple modes in your likelihood because there's different choices about what is and isn't an outlier, which will have comparable probabilities, and then you get multimodal crazy things. And then you can't really describe things with a single error bar at all. Now that kind of slightly goes off the reservation here, and we're not going to talk about it, but that probably is part of the intuition. But you know.
Thank you.
Everything I know about information theory, I learned but I said it all last week, literally, everything. I'm empty. Okay, now, good. There's another piece of introductory text that I should say, and that is that this is a beautiful situation where you could write down a likelihood, and then you could write down in closed form the optimum of your likelihood. In general, that's not true. Like, I don't know, but I don't think like the Higgs analysis from LHC was the optimum of the likelihood function. I think it was the optimum of the likelihood function late stage, but early stage they're running these triggers that like decide what events to keep and what events to delete. Those triggers are doing something very like operational that doesn't really refer to a likelihood at all. And so if you think about how the full data analysis stream from like collisions in the detector to the Higgs mass, it is not the optimum of the likelihood function. It's a much more complicated procedure that produced the Higgs mass. And so often, it's not even just that you can't make these assumptions. It's not like that at all. Your data are just somehow the output of some very complicated process. So sometimes there's just some kind of procedure that this procedure produced your estimate of your parameters. And a lot of us are in this state. Like you're doing EPRV, and a bunch of very clever grad students wrote a really ridiculously good pipeline that produces radial velocities for stars. You don't actually know how it did it. It doesn't really come down to a set of assumptions like this. All sorts of things happen in there of like dividing by the flat and figuring out the locations of the Fabry-Perot dots and like transferring those over to the spectrum. And all that stuff happened, and none of that really referred to any likelihood at all. And in this case, you can't take the second derivative of a log likelihood because you don't even have one. And this is a very generic situation in astrophysics because we do complex projects and they're very big. And Alex is laughing at me because Alex is like, none of my thesis applies in that case. Yes, that is true. Good, but we have higher standards for the cosmologists now. Okay, good. So this is the other piece of context. So one piece of context is these are not always correct, but the other piece of context is sometimes you don't even have assumptions like this. You just are estimating the best you can, and now you get a number. What do you do? Okay, so now we want to know what's the uncertainty on this number. We don't believe any of this, or we're doing crazy procedure. What's the uncertainty? So that's the goal of today. It's to find the uncertainty on the number. I'm going to talk about four things, although the fourth is really just there as a straw example, because we're going to go and talk about hierarchical models next week, and in hierarchical models we'll start talking about how you would really build a model of your noise as part of your project. So the four methods are Bootstrap, Jackknife, cross-validation, and what you might call noise modeling. And these two methods are known as resamplings, and they are unbelievably powerful And my current position is that even if you believe everything and you believe this uncertainty, you should still do the resamplings because they'll confirm your beliefs. And you can say to a skeptical referee, we even did Bootstrap and Jackknife and they confirm our uncertainty analysis. Of course, that's never what happens. Cross-validation is going to get at the relationship between fitting and regression. I talked on the first day about the point that statisticians often use the word regression when we're using the word fitting, but fitting and regression are slightly different things. Regression is when you want to predict new data. You want to use existing data to predict new data. Fitting, in my lexicon, is when you're using data to learn the values of parameters. These are parameters. You're using the data to get values of parameters. With regression, you're trying to use the data to predict new data. And in that case, you want to use cross-validation to assess your uncertainties. And cross-validation also is related to model comparison. And we are going to have a whole class on model comparison later. So I'm only going to just touch on cross-validation because it's really going to come back hard in model comparison. And the reason it's going to come back hard in model comparison is because I think all of the Bayesian methods for model comparison are completely wrong and wrong-headed. And I'm going to argue that we should be using cross-validation in any circumstance in which we are currently using the Bayesian evidence. And I'll explain in detail why that is. And it's a long story, and we'll take a whole class. And it's partly to break, astronomy is super Bayesian, and I'm being very careful to go back and forth and work both frequentist and Bayesian. And it's partly because the Bayesian tools are not always the best tools. Sometimes you do want to be using frequentist tools for important reasons. And it has to do with the fact that, it has to do with the idea that once things become extremely sensitive to your prior, you might want to back off and think about what the frequentist equivalent is. And cross-validation is very related to Bayesian evidence. You'll see why when we write it down on the board. And then the idea of noise modeling is now we can add the noise properties as model parameters. So the idea is if you don't trust these assumptions, you can parameterize your ignorance and fit for those parameters too. You can imagine you think there's outliers. You can build a model for the outliers, and then you fit for the parameters of your outlier model simultaneously with the model of your line or whatever. Now, this is discussed relatively extensively in the fitting a line paper, fitting a model. The fitting a model paper that I referred to last class, which is whatever, 1008.4686 or whatever it is. It's in the notes. It's in the top level notes. It's the homework for the first class. In the homework for the first class, I just said read the first couple sections of that paper. But as you read down into that paper, it goes into what do you do if you want to model these effects too, and it shows how you put in outlier models and model the noise and model intrinsic scatter and so on. So I'm not going to talk about that much. And the other thing that's happening here is that next week we're going to talk about hierarchical Bayesian models. And that is a great place to think about modeling the noise. And so next class is going to be fully Bayesian. So if I'm making you feel uncomfortable right now, don't worry, everything will be fine next week. It'll be extremely Bayesian. Also next week, if all goes well, there'll be a Jupyter notebook for the class, which means that it would be very good to make sure your laptop can run Jupyter and has NumPy installed. And we're going to try to make the exercise Python 2.7 versus Python 3 neutral. We'll see if we succeed. Yeah.
Maybe there's Azure Notebooks on the cloud where you can run stuff as well without installing it.
Good, yeah. There's ways to work entirely in the cloud, and we should check that we're consistent with that. That is a very important thing. In fact, we might be able to just use like the Google Collaboratory or whatever it's called, which Jake Vanderplas, former astronomer, is now developing. Good. That is a very good point. But it means next class, bring your laptop especially if it is installed with the things you need to do that. And if it's scaring you that I'm talking about Jupyter notebooks and NumPy and Python 3 versus 2.7, find somebody in the room you can sit next to, because you can work pair code would be fine for next class. Okay, good. Because we're gonna get real next class, where this is all. Okay, here we go. So let's introduce. So I'm just gonna explain how Bootstrap. We're actually gonna start with Jackknife. Jackknife is so beautifully simple. Let's start with Jackknife. So let's do it. Jackknife. And by the way, the Wikipedia pages on resampling are excellent. In fact, I consulted them this morning to get certain dimensionless factors right. You'll see the dimensionless factor in a moment, that you can imagine I never remember. And I never remember it, and then I just always look it up on Wikipedia. Someday somebody's going to edit it to put a sign error in, and all of my work will be wrong from then on. So the idea of Jackknife is you have your estimate, which you got however you got it from your data. And now what we're going to do is we're going to make what I'm going to call leave one out resamples of your data. So meaning you're going to take your data, but leaving out one data point. Now, what's a data point? This does depend on an idea of what a data point is. And of course, there's no such thing as a data point. But anyway, you kind of have a sense of what a data point is. But actually, if you really drill down, we had this great talk yesterday about how the fact that you can't even figure out the velocity of a black hole. You don't even know the velocity of the black hole. You also don't know what your data point is, it turns out. And so we have a lot of freedom here about what a data point is. A data point could be just part of your data. It could be a tenth of your data. Could be considered one data point. You can do k-fold things of this. You don't have to do every data point individually. Like if you have a billion data points, this sounds like you have to make a billion leave one out samples, which you don't. You can make whatever one, because you can count a huge collection of stars as one data point. So anyway, but you leave one out, you leave out one of these data points or data clumps, and then so the one we're gonna leave out, so we're gonna leave out samples, I'm gonna call them sample M, because and that's the sample of my data leaving out part M. So this is all the data except M. And then I'm going to make theta hat M using SM. So using the subsample that leaves out point M, I'm going to make an estimate, which I'm going to call theta M. And then I'm going to do that for every possible opportunity of throwing out data, you see? So what I'm doing is empirically asking, how sensitive are my measurements to each individual part of the data? Because if I leave out a little bit of the data, I can still do my estimate, just with less data. Not much less data if I do 12 of, typically I do 12, by the way. My standard is, well actually in my group, everything's supposed to be power of 2, so we either do 8 or 16. But then we always are arguing about whether to do 8 or 16, and then we compromise to 12. But anyway, roughly 12, cut your data into 12. Each 12th you leave out, that's your leave one out sample, S sub M. From that 11/12ths of your data, you produce this thing. And so now I have, in addition to my estimator, I have 12 additional estimators that reuse most of the data, but not all of it. And they're all slightly different. And now you have a sense that the variance of those estimators that you have must have something to do with the noise in your data. Yes?
I think I have a guess as to the answer, but when I'm choosing the 1/12 to take out of my data,
Yes.
do I have to randomly choose this one?
Oh, what a great question. You've anticipated a whole section of this class. Because you can imagine, I deliberately and beautifully didn't say anything about that. Do you choose it randomly or not randomly? And we're going to come back to that. But you can imagine you might choose not randomly because you might be worried that there's some kind of like calibration gradient in your survey, and so you might drop your survey in slices because you think there might be a calibration gradient. In fact, that's exactly what we did in the baryon acoustic feature paper I was talking about last week. because we were worried that calibration might be projecting onto the Variant acoustic feature. However, a lot of statisticians I know say you should just choose it completely randomly because the random number generator has better intuition than you do about what's wrong with your data. Which is not unfair, although it is insulting. But yes, that's insulting, but I'm happy to insult you that way. But one problem with that, though the statisticians are not wrong, it would be hard to do enough combinatoric trials to actually learn what's wrong with your data by just doing random samples.
There's another use case, though, that's worth pointing out. It's where there's cosmic variance.
Good. Good. Glennis just mentioned cosmic variance, which is a very important idea here, and I did not think at all about the point that I should bring this up in this lecture. But one of the things that's beautiful about Jackknife is it will, if you cut up your survey by volume or by contiguous volume and make your estimators, it also accounts for cosmic variance. It will correctly both account for your noise and some part of your cosmic variance. And of course won't
measure the amount of cosmic variance.
In principle, yes, you can directly measure the amount of cosmic variance through such tests. Although, of course, only on certain scales, because it won't tell you the variance of this volume versus a completely different volume, but it's some of it.
But this was, I mentioned it apropos of choosing what to leave out.
Yeah,
Because
good.
the way you phrased it sounded like the ideal would be to leave out 1 star out of a billion if you could afford to do it. But for many purposes, that's not accurate.
Good. Glennis is saying, I'm just repeating for the audio, Glennis is saying, if you know that you have cosmic variance in your data, you're going to want to chop it up in a way that will be sensitive to the cosmic variance so that you can see it. And then, in fact, you should have a situation where if you cut it up by volume, you'll get one uncertainty. If you cut it up totally randomly, you'll get a different uncertainty. And the difference between the squares of those uncertainties should be, to order of magnitude, your cosmic variance, which is cool. Of course, it might also be calibration issues, which is what we were worried about in the Variant acoustic feature. Yes?
I'm sorry, but what is cosmic variance?
Cosmic variance is the point that in the universe, there is structure on all scales. So this volume will be different from this volume just because literally we are one draw from a set of initial conditions that has variance on all scales. And cosmic variance is the limiting noise source in the CMB now on large scales. So CMB L's out to, I don't know, 100 or something. It's now no longer photon limited, it's cosmic variance limited. It's really the fact that there's only one universe to look at that limits our ability to make inferences, which is a little scary when you think about frequentism. Yes, that's one reason we're all Bayesians, I think, by the way.
I don't know if this is the right time to ask this question because it relates to both resampling methods you talked about.
Yeah.
But what if you're, so, you know, I've used this kind of thing when you have, like, you're estimating a luminosity function. You have a bunch of luminosities of galaxies, you leave one out, you can do it again, or whatever it is. But what if you have very structured data? So you mentioned the radial velocity case, right? What if you have a spectrum and you have flux versus wavelength on a nice wavelength grid, and you want to, you have some line, you want to measure its centroid or whatever. Do you literally leave one wavelength out?
Good.
Or in the resampling, do you literally resample all those wavelengths?
So Saurabh is asking, if your data are highly structured, if your data are just individual data points, it seems obvious how you leave them out. But what if your data is like a continuous spectrum of a star or a continuous image of a galaxy? Do you just leave out some pixels? And the answer is yes, you just leave out some pixels. Now, of course, the EPRV crew used a shell spectra where you have different orders, and so now you can leave out orders, which are kind of big contiguous chunks of spectrum. If you have this gets into the details of what you think is important. So I think what I'm going to end up advising everybody is that if you think something's important, you should cut on that quantity, and you should also do a random cut. And you should compare the two answers you get and go with the more conservative. Okay, so for instance, when we do spectroscopy, in principle, we could just drop a random set of pixels when we cross-validate or when we do Jackknife. But we kind of have a sense that the information in the spectrum has a finite resolution. So it feels to me like we should cut out chunks of the spectrum that are substantially larger than the resolution of the spectrum. And if we do that, And then if we got into a fight, I would just say, let's just do it both ways and see what happens.
Well,
so I would cut out chunks of spectrum and ask, how well do I measure the velocity?
Let's say you have the shell spectrum where you have a lot of basically no information pixels where there's no spectral line, and then you have a spectral line. And
Exactly.
if in many of your Jackknife samples you're leaving out a point
Good.
which had no information.
We are going to come back. I'm going to come back to that exact point in a second. It is whether you use Jackknife or Bootstrap depends a lot on whether the information is uniformly distributed through your data or non-uniformly. So I'm going to come back to that exact point because I'm going to write down the formula for Jackknife, then I'll write down the formula for Bootstrap, and then we'll talk about which one we use. If I don't answer that question, re-ask it. Same question. Okay, good. Okay, good. So now you've made these leave one out estimates of your parameter. They share, you might think, well, the variance of this is an estimate of your noise. It's true, the variance of these is an estimate of your noise, but it is not a raw estimate of your noise because it's reused most of the same data. You see how these different estimates are actually highly covariant? So when we combine them, there's a dimensionless factor, which I have to look up on Wikipedia, to combine them correctly. And so let me be very clear here. I say we've made capital M, leave one out samples S little m, right? So I'm doing M samples, capital M samples, each of which is indexed by little m. I generally do this. Big things are numbers and little things are indices. And so then the Jackknife estimate on your error on theta, your uncertainty on theta, is, I have to look at my dimensionless number. God damn it, did I write it down? Oh yeah, there it is. It's m minus 1 over m. Don't ask me to derive that. Times the sum of m goes from 1 to your full sample of theta m hat minus theta hat squared. See how this looks like a variance? You're summing up the squares of differences, looks like a variance, but instead of dividing by m, you're multiplying by m minus 1 over m, and that has to do with the fact that the different samples are highly covariant, and this corrects for the covariance. Everybody good? This is a beautiful way to estimate your uncertainties.
So if you do this very often, then you can essentially drop the prefactor.
Exactly. So if you're doing the whole Gaia data and you have a billion things here, and you have a billion, this prefactor is 1. Which is beautiful, and if you understand why it's, if you sit down, like you go out to the park and sit by the dog run and think about why it's 1, you will figure it out. It's beautiful. Yes?
Can you just say again what the big M was?
Big M is the number of these leave one out samples I made. Each of which leaves out 1/mth of the data. So I have m leave one out samples, each one leaves out 1/mth of the data. You have to do the complete set, by the way. You're not allowed to cheat. You must do the complete set. If you don't do the complete set, it's a different prefactor, which I'm not going to say. Meaning you have to, if you leave out an mth of the data, you have to do all m leave 1/mth out, and they have to be disjoint and all those things. It has to meet all the criteria. So just read up on the criteria and execute. But it's very straightforward.
Would these be the overlap randomly selected or orthogonal choices?
These m choices have to be orthogonal. They have to be exactly orthogonal and complete. When you add them up, it has to be your whole sample.
Then you can derive that in your head.
And then you will be able to derive this prefactor.
If you were duplicating it.
If you're duplicating, that's what's going to happen in Bootstrap in a second. Now, notice that this thing sort of required, as we just were talking about a second ago, inspired by Sarab, that these different subsamples are kind of equally informative. Imagine one dropped out piece of data was carrying all of your information. Then you'd be fine, uh-oh, fine. And then this distribution of these differences would look horrible. So it is a very good idea to visualize these differences. Because if you have a situation, let me start back on the other side. I don't want to go too far down because of my lines of sight. But if you plot these thetas, Oh, by the way, I haven't said what the vector generalization of this is yet. Don't let me forget to do that. If you plot these thetas, and here's theta hat, your original measurement, and now you plot the m things, here's disaster. Oh, what you want to see is this. These are your theta m hats. Okay? What you don't want to see is if that's what you see, you need to bootstrap, not jackknife. So this is bad. Here's another thing you don't want to see. Although if you do see it, you will learn a lot. Here's theta hat. Here's your theta m's. That, you might think, how could that ever happen? This happens a lot. If you have a biased estimator that is only asymptotically correct, then as you remove data, the mean will also shift. And that's a very common thing in procedures. If you have a procedure by which you've generated your radial velocities, that procedure might be very signal-to-noise dependent, and therefore it might drift off, and your jackknives will look like this. That is very interesting because if you're really gutsy, you can use this to infer things about your estimator. But the short answer is you should be worried if you see that. That means there's sort of something wrong with what you're doing. Now, it's not necessarily uncorrectable, and if you go to the jackknife page on Wikipedia, they talk about this exact case as a way you can learn certain kinds of asymptotic biases. But that's out of my expertise. Basically, I'm looking for this. If I see this, I go to Bootstrap. And if I see this, I also go to Bootstrap. Both of these things make me want to go to Bootstrap, which we're going to talk about in a second. Yeah.
So I mean, you know, often these things are multidimensional. Do you then visualize sigma m minus sigma
Good. Let's
absolute?
multidimensional. Yes. Good. I'd already forgotten. I just said I needed to do that and immediately forgot. So in general, in cosmology or in astronomy, our parameters are not single parameters. We have a vector of parameters. And if you have a vector of parameters, instead of doing theta m minus theta squared, you do theta m minus theta m minus theta transpose. Remember, for me, vectors are always column vectors. So this is the outer product of the two things. So this generates a Hermitian rank 1 matrix. And then when you add up all your m trials, you get a rank m or d matrix, depending on whether m is larger or smaller than d, where d is your dimension, whatever. Big deal. If you are doing this, if you are doing vectors, you generally need to do a larger jackknife if you care about anything more than the first eigenvector or whatever of this matrix. Basically, you're only going to estimate the top eigenvectors of this matrix well. You're never going to estimate the small ones. Yeah?
Looping back,
Yeah.
why would you use Jackknife instead of Bootstrap at all? Why not just use Bootstrap if it's more robust to these kinds of issues?
Well, it's a good question. It's funny because I always want to do jackknife, I was asking myself this morning and I wasn't coming up with a very good answer. I always do jackknife if I can. If these don't happen, I always use jackknife, and I think the reason I use jackknife is because it really uniformly uses the data. It's very, very even in the data. I don't have to worry about whether combinatorically I hit some weird freak. It really is just everything gets used in exactly the same proportion. Whereas when you do Bootstrap, you hit a combinatoric, there's a combinatoric set of choices you could do in Bootstrap. You'll never hit the worst combinatoric choice. And so maybe you're missing something, and then some data get reused, and maybe you just got unlucky, and whatever. So jackknife just feels a little more systematic to me, but I do think that almost any pathology you hit says you should go to Bootstrap. Let me follow that up with one more thing, which is if you do have this situation, you should look at that. So if you were naively doing radial velocity and you had a spectrum and there's only one line in it, this is going to be the chunk of your spectrum with that line in it. you know, or whatever. One thing that I think is really nice about these resampling methods is they produce visualization opportunities. You can visualize things about the data. You can ask, when I'm biased low. You can also say, what's different about the jackknife samples in which I'm biased low versus the jackknife samples in which I'm biased high? You can ask those questions, and you can ask, are there parts of the data that are pulling me low and pulling me high, and maybe you'll learn something. Often you learn something by looking at your resamplings. And in principle, you could have learned it by looking at the raw data, but sometimes the individual raw data points don't somehow contain enough information to see it, but the jackknife does. Anyway, there's a lot of reasons you want to use the jackknife. Treat it as a sandbox that you can play with. And that also relates to this point that if you can think, well, because of cosmic variance, I want to cut it up this way, and because of statistician friends of mine, I want to cut it up randomly, do both and compare them. And you should see the differences, and it should be interpretable. The differences should be interpretable. Good. OK, great. This fact is going to apply also to Bootstrap. Everything's going to be the same. Bootstrap is almost identical. So Bootstrap. Oh, by the way, I said there are proofs, or there's literature and proofs that these are asymptotically correct. Those proofs don't rely on very much. The main thing they rely on kind of two things. One thing they rely on is that when you cut out the data are kind of independent, which relates to why cosmic variance says what you should be doing. If you were cutting out data that is highly covariant, there might be issues. And that's one of the reasons why if you have a spectrum, you probably don't want to cut out individual pixels. You want to cut out chunks that are much bigger than the line spread function. So they have a kind of independence assumption underlying them. And then the other thing, they have a kind of stationarity assumption underlying them, meaning no data point is special, that all the data points are kind of similar and drawn from the same distribution. And both Bootstrap and Jackknife have some kind of assumption like that underlying them. It is too much for me. I don't actually know. That's real stats. And that's truly stats to understand when Jackknife and Bootstrap are justifiable and what their provable properties are. OK, Bootstrap is the idea here is that you have n data points. Maybe I should still call it m, but I want to be very clear that you have your full set of data. You have all of your data. And now what you're going to do is we're going to pour all the data into an urn, because in statistics it's always an urn. I don't even know what an urn is. But anyway, apparently it's something you can reach into and grab a data point. So you reach into the urn, shuffle it around, grab a data point, then you record what data point you have. Then you throw it back in, shuffle it around, grab another data point, record it, throw it back in, shuffle around. And you do that n times.
Isn't an urn that attaches to the dead person or story?
Yeah. Yes, that is one of the things urns are used for, yeah.
So you're saying you killed your data.
Yes, you burned it. Yeah. And when I have to ask my grandmother questions, that's also what I do. Maybe that was offensive. Anyway, what you do is you choose n data from your data with replacement. What's called with replacement, meaning when you choose the data point, you now throw it back in the urn so it could get rechosen. So every time you do this, some data points get skipped, other data points get doubled, some even get tripled. It is a Poisson resampling of your data. Now, you can see intuitively why this is a good idea. It assumes that your data are a representative sample of your data. And now by resampling it, you're getting a representative sample of a representative sample of your data. So you can see how this will flow down to some kind of provable properties for this. But it is a little weird because it seems like, where's this coming from? And it does make assumptions, and in particular, the stationarity assumption is a little weird, and I don't really understand how it comes in. So if you have this probably, yeah, somehow it does connect to the deep assumptions of your model, in which I don't really understand. But this is a very robust, very easy to execute problem. This is super easy to execute. So for many, of course, if you're dealing with spectroscopy and you want to take parts of your spectrum and not other parts of your spectrum, you might have to fix your pipeline a little bit to be able to do that, because most pipelines are expecting the whole spectrum to be there. So sometimes you have to do a little work, but if you've done your data analysis, if you've made your data analysis such that the data can be weighted, like so that the data, like you can weight the pixels in your image by the uncertainties, you can actually just use Bootstrap to get you new weights, and then you zero weight some of your data and you two weight other parts of your data, and then you just redo the same thing with the new weights. So if your data pipeline already includes weights, you can actually just use Bootstrap as a way to reset the weights and then rerun. There are some contexts you can get where it's very easy to execute Bootstrap. And then when I choose these n data, I am now going to produce a estimate theta m. I'm going to do this whole thing m times. So m times. Notice m and n aren't the same here. I might have a billion data points, but I only do this 12 times. That's fine. You just, as many times as you can afford to do it, you do it. Now, there is a combinatorics issue here. And if you have any significant data set, the combinatorics here for your Bootstrap is much larger than the domain of your random number generator. Hold that thought for a second. I'm going to get you. And in fact, there's a group at Berkeley that's looking at this question of whether bootstraps are somehow biased by the fact that random number generators don't literally have enough domain. Like, this is truly combinatoric. Like, check out how combinatoric this is. Oh my God. Like, you could literally bootstrap like with all the computers on Earth for the rest of your life, and you would never touch all the opportunities you have. So there's a weird combinatoric craziness here, but the proofs for Bootstrap do not rely on you fully expressing that. Yes, you had a question?
Yeah. When you say you're going to do it m times, are you sampling from the data that you generated?
So let me be very clear. You have n data points you took in your experiment. So if you want to make it easy, let's just imagine there's n stars in Gaia, and you're looking at their common proper motion or whatever. So you have n stars, and you're measuring their mean proper motion. Now what you do is from those n stars, you choose n with replacement, and you measure their mean proper motion. Then you throw them all back up in the urn, shake it up, do it again, do it again, do it again. So you do m identical trials of this operation. So you get m new estimators of the proper motion of your collection of stars. So you have the overall estimate, and then you have m bootstrap estimates. Yeah?
So when you're doing this, so for example, you have your proper motions that are like 2, 3, and then 5. 4 is never a proper motion. Will you ever get 4? Not ever.
If it's not in your original data, no. Good. The question is, like, what if your data are like somehow gappy and you'll never fill in the gaps by doing Bootstrap? That is true. One of the assumptions of Bootstrap, which I actually just stated maybe a few minutes ago, is that your data are a fair sampling of your data, of the data you could have. So the idea, I think Bootstrap is exactly correct. If your data are a fair sampling of the data you could have, and some asymptotics, like, and you have a hell of a lot of it, then I think Bootstrap becomes exact with some assumptions. Yeah.
I'm trying to understand why you would ever use Jackknife over Bootstrap. Because even if, like, for example, if you have a small data set and you want to calculate the mode of it, Jackknife could give you the exact same mode every single time.
Yeah.
And you'll have a variance of 0.
Yeah. No, it won't. It won't. But you're right that it feels like it could. Good. So the question is, why would you ever use Jackknife over Bootstrap? So I have some answers to that. Let me say a couple things. First of all, you actually brought up a very interesting model, which people in the room might not have thought about. Imagine you have a set of data, and you're taking the median of those data. Now, if you think about your Bootstrap trial, or the mode, actually mode is an even better one. So you're taking the mode of some data, which is just an absurd thing to do. Don't ever do that. But imagine you were. Then it is true that many of your Jackknife trials will give you exactly the same mode. But then you will in general hit this case, where everything will give you exactly the same mode, and then one will like fly off. But if they all give you exactly the same mode, then to that level of precision, that you have no uncertainty on your mode, and Bootstrap would do the same. Like if Jackknife always gives you the same mode, Bootstrap will also always give you the same mode. You can check it. I mean, in principle it wouldn't, but in practice.
You have a histogram of just like one sample in each case, and one has two. One is like two samples in one grid plane.
Then neither
Jackknife would give you the median if you exclude one of those samples, and then the exact same mode every other time. Whereas Bootstrap would give you a whole spectrum of modes.
You might be right. There's some pathological cases. Miles is bringing up pathological cases in which Bootstrap and Jackknife might give different answers. That is a good question. I would have to think about it. Most data analyses don't fall into that category, so that isn't really a problem. However, one reason you might, I think really when you look back at this, there's two reasons to use Jackknife over. I agree in general. If you're worried about the structure of your data, you don't know how non-uniform it is, you don't know what's going on, use Bootstrap. I totally agree with that. That's my basic advice. However, if you believe there's structured noise in your data, or there might be structured noise, Jackknife allows you to very systematically cut up your data along the axis where you think there might be noise, like the cosmic variance case. You can cut up by volume, and you know you can be sensitive to that. Or if you took data at different air masses and you're worried that you didn't correct for air mass correctly, you can cut up by air mass, and you'll just see it in the Jackknife samples. Whereas in a Bootstrap, you won't necessarily see it. I mean, in principle, you could, because you can visualize them and then figure out what their footprints are of the data, and you can get it. But in practice, Jackknife's going to be better for kind of visualizing it. So I think Jackknife, and then the other thing that I said earlier is that Jackknife uniformly uses your data completely democratically, whereas Bootstrap does not and cannot. And so I think it really depends on how uniform and equal information you see your data as being. And as you're kind of implying by asking about different kinds of statistics, there might be certain statistics where it's kind of really inappropriate to use Jackknife. I don't know. I haven't really thought about it. It's interesting to go adversarial against Jackknife, which is more or less what you're doing.
But in those Jackknife examples, you were sort of using your intuition about what's wrong with the data contra the statistician's recommendation.
Exactly. Right? So I think my view is not the same as the statisticians. I believe we do have a lot of intuition about the data, and that you should chop Jackknife samples along any axis that you are worried about. If you think air mass should have nothing to do with your conclusions, and you took data at different air mass and you're worried about it, you should cut by air mass. And if you think there's cosmic variance, you should cut by location. Or if you think there's calibration issues, you should cut into the sky into regions that are calibrated independently or whatever. I think, and then comparing those will be interesting. And that, I guess another thing I would say, which is relevant to both your question and Miles, is that Jackknife gives you lots of ways to visualize things, because it's not just that you can look at how they ended up. You can literally ask, which left out subsamples put me here and which left out subsamples put me there, and map it back into your data set and visualize it. So it gives you a lot of opportunities to visualize where are the issues in the data with your model.
If you have a heavy tail distribution, that's better. So you have a risk of undersampling.
The question is about heavy tails. If you have heavy tail distribution, you have this danger that you'll never sample into these tails, and you might just be wrong about your errors. Neither of these methods will protect you from really bad heavy tails. However, this kind of result implies that you do have heavy tails. So if you get this kind of result in a Jackknife, and you can also do the same distribution for Bootstrap, and it will also be the case that a Bootstrap would show some craziness if you have heavy tails, if you bootstrap enough. But there's no guidance on what's enough.
So what's M? What's good M based on M?
Good. What is M? So if you believe that things are fairly well behaved, and if things look pretty well behaved, then M, I think, and you're only doing one parameter, then M of order a dozen is fine. But if you start to see some oddities like this, I think you want to bootstrap pretty hard and try to understand whether this is heavy tails or one bad data point, or like you want to try to understand where that's coming from. So I don't really have a guidance on how many. If you're doing a one-dimensional problem, 12 is like our standard thing that we do, unless we see something weird, and then we do more and also look at distributions. But I don't really, unfortunately, just like MCMC, these methods do not come with guarantees at finite. These only come with guarantees at in asymptotics. They only have asymptotic guarantees, no finite guarantees. Yes?
And then your recommendation, if you're fitting, Cirsic profiles to galaxy images, just resample, have a couple pixels show up more than once. And...
Right, if you're fitting, no, and we've literally done that in SCSS. We've literally, when we're fitting profiles to galaxies, we just drop chunks of pixels from the images, large enough chunks that they're bigger than the point spread function because we want the data to be kind of independent, but small enough that they're smaller than the galaxy. And then, of course, sometimes you get to really small galaxy images, and then there really aren't that many options. By the way, both Jackknife and Bootstrap, well, Bootstrap not so much, but Jackknife, you can do with twofold, and we often do. Imagine your estimator is really expensive, and you just can't afford to do it many times. Sometimes we just split our data in two and treat it as two surveys, and the difference between those two surveys is just some kind of estimate of where we're at. Now, technically that's like not a good error analysis, but sometimes you just can't afford to do estimates at huge effort. Like you just can't afford it. Like imagine you were doing that for billions of galaxies, and some of them are really tiny. You're just not going to be able to do like a 24-fold cross-validation or whatever on every one of the galaxies in your huge sample. And so you have to make some decisions about where you go. So there's some pragmatics here as well. And remember, something I emphasized last class, and I will emphasize over and over again, though it is incumbent on you as a physical scientist to deliver a number with an error bar, it is not incumbent on you for that error bar to be precisely estimated. If it was incumbent on you, we would have to retract the entire astrophysics literature. So you just have to do due diligence. And I'm really recommending that strongly. The point of this class is not to slow down your research. It is to make your research more justified. And if a referee says you did not do enough bootstrap trials, do twice as many and tell them to shut up. Don't do E to the number.
At the same time, if you're not correctly estimating your uncertainties and you're using those values to then derive something else, your models will have a harder time fitting. You're throwing away data if you're radically wrong on your...
Yeah, so Brewer is pointing out that if you are wrong about your uncertainties, it will have downstream consequences and it will change or reduce the value of your data going forward. That is absolutely true. And so the question of how careful you have to be about your uncertainties is a subjective question that is about your goals with your data. And one thing that we're going to talk about, and I mentioned it on the first day, but it's going to become a theme as we go, and it's going to become more and more of a theme, is subjectivity. So, and I said it on the first day, data analysis is fundamentally subjective. What you write down as your model assumptions are always subjective, and what your intentions for your analysis are subjective. We like to think that we're like objectively learning the properties of the universe. We're not. We're making subjective decisions about what's important, and how well you need to do your data analysis is a subjective question, and it does have to do with what your uses for your analysis are. Some people would take this Planck data and try to make a map of gas in the Milky Way. Other people will take the Planck data and try to figure out the cosmological parameters. Those two people have very different error analysis needs, because our understanding of the galaxy is extremely imprecise and our understanding of the cosmological model is extremely precise. So it depends on all sorts of downstream use case things. So I'm agreeing with that 100%. That's a very important point, and you have to make a judgment there. And if you don't see how to make that judgment, it's time to step back and think about the design of your project again. Sometimes you don't know how precise you need it to be, and then that's a question then you have to come back and ask yourself, how would we answer that question? And if you can't answer that question, there's something missing about why you're doing the project you're doing. But of course, we're often in that state. I'm not saying you always have to know why you're doing a project. Otherwise, then we all become existential wrecks and we end up at the bar. But there's a balance.
You always end up anyway?
Yeah, also when you have success, too.
Following up on this point, I find it strange that many astronomers say, the errors are wrong, because they're always wrong, right? They're always just approximations, or it's always a model to reality, or to our experiment.
Kurzendorf is saying...
Is this only me thinking that many astronomers think this, or do many astronomers really think that there's a correct way, and then you get the right answer?
Kurzendorf is saying people often complain, oh, the errors in this paper are wrong, and his reaction is kind of, aren't they always wrong? And yes, it's both true that the uncertainties in every scientific paper are wrong. In fact, all model components are wrong at some level. We don't have access to God's truth. Even lambda CDM is probably not God's truth. And in particular, error estimates are wrong because in order to assess them, you need immense amounts of data because you need to be able to go to fourth moments of your data and things like that to understand, or fourth moments of the distribution from which your data are drawn. So if you do inferences about fourth moments in order to understand your problems with your second moments, yada, yada. It's a mess. So it's both the case that people are doing their best and the error analysis in our business is generally very good, and it's all wrong. Both of those things are true, and that means that if your model doesn't exactly go through some measurements that are in the literature and it's just outside the error bars, you know, people often write down what's chi-squared per degree of freedom. You see it all the time in papers. Oh, it's a good fit because the chi-squared per degree of freedom is 0.98 or whatever. And I'm always like, but I don't believe the uncertainties that went into that, and they went into that squared. So I don't think we should be making major conclusions about how the world works on chi-squared per degree of freedom. And that relates to this point that these things are never known that accurately. I think if you're in the order unity ballpark, you're good. But by the way, that is controversial. There's a lot in the astrophysics literature that really, they'll say, well, this model has chi-squared of 1.4 per degree of freedom, and this model has 0.98 per degree of freedom. And first of all, chi-squared per degree of freedom, it does not translate into a likelihood ratio. And second of all, it depends unbelievably sensitive on the noise. Yeah?
I just wanted to comment, there's many kinds of noise, and that comment, the idea that it should be 1 per degree of freedom is postulated on as being measurement uncertainty, but very often it's what I would call astrophysical noise.
Good. Glennis is pointing out that many of these arguments about error bars or chi-squareds or anything is kind of thinking about the noise as being measurement noise, but in reality, there's lots of other problems with these models, either mean problems with the model or variance problems with the model, because astrophysics is complicated. And there's all sorts of gastrophysics that, you know, if you're measuring stars, there's all sorts of gastrophysics stuff that comes into your model of stars that's not correctly modeled, can't be correctly modeled, it's part of the noise. There's also covariant noise, that if you've calibrated some part of the survey wrong, that wrongness of calibration is spreading all through the survey in some structured way, and it's not captured by your measurement noise.
But minimizing chi-squared to get the best fit parameters can still be the correct procedure.
Exactly.
It's just your idea of how to interpret the chi-squared degree of freedom.
Excellent. Glennis is just summarizing almost my whole philosophy. She said, but minimizing chi-squared still can be a good idea because it gets you good estimates, and then you just have to be more open to what the noise properties are. I agree completely. And since we don't believe all the assumptions that go into our likelihood functions, we still might want to optimize the likelihood to get an answer, because then we know that our answer is correct under certain assumptions, but then we just remember that those assumptions are probably in detail wrong, and we can test them or modify them by doing empirical methods like this. I agree with that completely. That's a perfect statement of my view. You should make a set of strong assumptions about your data so that you get a well-defined procedure for making your measurement, and then you should be open empirically to discovering what its noise properties are. Correct. Good. That is exactly the point. Okay, good. I didn't even complete what you do with your bootstrap samples. Let me just say, in your bootstrap, and we're about to get to cross-validation, and then we'll say a few words about modeling, and then we're done. So in bootstrap, your uncertainty, sigma squared on your parameter, is set to be 1 over m, because we did m of these trials, and maybe people would argue about whether it's 1 over m or 1 over m minus 1. I'm not going to discuss that. M equals 1 to m of theta m minus theta m minus theta squared. It's just the variance. So the nice thing about Bootstrap is because the assumption is that your resamples are just representative samples, it turns out the variance, it's just the variance of the Bootstrap trials is your variance. And if you're suspicious of that, it speaks highly of your intuition, but you're wrong. Turns out it just variance. It is a paradox that that's true. And I think it is only true asymptotically in some sense, but that's what is used as the bootstraps. It is worth remembering that there is a certain sense in which Jackknife and Bootstrap still underestimate your errors, because Jackknife and Bootstrap only show you the uncertainties that are implied by the data you did get. But there's some uncertainty that's coming in from the data you didn't get, especially if you're heavy-tailed. As was mentioned here, if you're heavy-tailed, there might be certain data points that are relevant to your measurement that you'll just very rarely get. And so they just weren't represented in your sample, and then they're not represented in your Bootstrap or your Jackknife, and so in that sense, your Jackknife or your Bootstrap is slightly wrong. So that's why the sort of proofs are all kind of asymptotic. Okay, good. Questions? We're about to move on to cross-validation.
It's the same vector replacement.
Yes, good, same vector replacement. If you have a vector, you do this, and then you have to do a lot of Bootstrap trials. It gets expensive fast. And if you really look at the density, if you are really trying to estimate a large covariance matrix, there's results in density estimation, and the results in density estimation suggest that once you get to 10 to 15 dimensions, it becomes physically impossible. So if you have a 15-dimensional covariance matrix, which many people in cosmology do, you do not know what it is from any empirical method. There's no empirical method by which you can figure it out. That is a mistake that's being made in some parts of literature. That's why these methods are much better to use for small parts of your analysis, just to find out the uncertainty on the Higgs mass, or just on sigma 8, or just on one parameter at a time. If you really need to know the covariances of all your parameters, it puts a very heavy load on these problems. They won't generally be possible. But you can do pairwise. If there's only two parameters you care about, you can take their estimates, and then you can use this to work out the covariance of the two parameters. So you can take any pair of parameters and work out the covariance this way by doing this on 2 vectors, and then the 2 by 2 covariance. That you can learn very accurately. But once you get to like 10 by 10 or 12 by 12, you're done. We won't be able to do it. Okay, good. Cross-validation. So I'm just going to sketch cross-validation, and I'll just sketch it and then give a sense of what it does, and we're going to come back to it later because it's going to come into model comparison. So I'm going to really push it off to model comparison, and that's where it shines, and cross-validation is just a beautiful tool for assessing model comparison. And if you have almost any data analysis you do has hyperparameters. Like, for instance, you decide to fit the traces in your spectrograph with a cubic polynomial. Cubic is a choice there. Polynomial is a choice. Or you are modeling some nuisance as a set of PCA eigenvectors, like you're doing Kepler light curves and you're using 50 eigenvectors you've generated from other Kepler light curves to model the noise. 50 is a choice there. Those choices are very well assessed with cross-validation. In fact, I believe there's no method other than cross-validation for making those choices. And you either go heuristic or cross-validation, that's it. In principle, you can do other things like Bayesian evidence or whatever, but they don't really work. So cross-validation is very useful for making those kinds of choices, but it also tests the accuracy of your predictions in the data space. So that's what I'm going to talk about here, because that's a noise question. And if you want to see a recent example by me, there's a paper by me and Christina Eilers and a few others. and where we do distances in Gaia, and the way we figure out the assessment, we assess the accuracy of our distances is cross-validation, because there's no other kind of way to check the accuracy of your predictions. So, because in Gaia we don't have truth. We don't know the true distances to anything, so we have to. Okay, and so the idea of this is here's X and here's Y. I have a set of data like this, and I fit some curve to the data. Now I want to ask, how accurately do I predict? How accurate is this a prediction of these data? Or how accurately does this describe the data? Or could this curve be used to predict new data? And these are the data you have, so you can't actually ask how well does it predict these data, because you use these data to fit it, and so duh, it predicts them pretty well. So cross-validation solves that problem. How does it solve it? You take this data point M, you exclude this data point, you fit the model excluding that data point, and then you predict the left out data point given the exclusion. And now do you see, since we didn't use this data point in the fit, we're just checking it, it is a true prediction. The model is trying to predict this data point given the other data points. And then you cycle through and do that for every data point. And that's called cross-validation. And the nice thing is it has a bunch of great properties. One property it has, if you do this in a principled way, it really is answering the question, can you predict new data from old data? Because you're leaving it out. You can even do things where if you think things aren't stationary, like you're doing finance and you're trying to predict the price of a stock, you can use past data to predict future data. You can structure this in whatever way you want if you think there's like causal issues in your data that, or non-stationarity or whatever. So you can actually do a lot of interesting things with cross-validation, and there's a big rabbit hole to go down if you look at cross-validation. It is the premier method for machine learning. That is if you can afford it, this is the way machine learning methods are tested. Especially in frequentist machine learning, but even in probabilistic machine learning, it is basically, cross-validation is the premier tool. And it is a beautiful idea because it really does directly emulate prediction of new data. There's another thing I want to say, which is that if the way you assess if you're just interested in uncertainties, you can say, well, this point I mispredicted by this amount. Oops, that's a delta y. I mispredicted by this amount, and then you can ask what's the variance of those offsets, and that would be an uncertainty on your prediction. So that's the first thing you can do. But the next thing you can do is if you have a likelihood function, you can actually ask what's the likelihood of this point, the probability density at this point, given the fit you did to the other points. And you can product those, and then you have something that has interpretable probabilistic properties. And in fact, it looks very like the Bayesian evidence. The calculation you end up doing here looks a lot like the Bayesian evidence, but it is purely frequentist. It is frequentist safe. There's you never are doing an integral over parameters. You are never putting down priors. So it is a purely frequentist but probabilistically interpretable assessment of the quality of your model. So there's two ways to think about it, and they're both relevant. For the purposes of this class, this is an empirical estimate of the uncertainty of your prediction. For the purposes of a class that's going to happen in a few weeks, it is assessment of the goodness of fit of this model, or the appropriateness of this model to these data.
I want to just, it's very closely related to the chi-squared, but.
And you can even produce a chi-squared here.
It ought to be smaller, I get. Oh no, it's not clear.
It's complicated. Oh, by the way, the reason people use it for model selection is if your model doesn't have enough capacity, it does really badly. Like if you have this model, if your model has tons of capacity, so it can go through all the data points, it will in general deviate at the location of any individual one if you leave it out. So that's why cross-validation is used for model selection. But we're not talking about model selection today, so we're just talking about accuracy of prediction. That's how we use it, by the way, in this paper. I think it's just Hogeyers and Ricks now that I say it. It's the recent paper that's by us. We use cross-validation to assess the accuracy of our predictions. Yes, Danielle?
So is the only difference with Jackknife the fact that you select just one point and trying to fit, as opposed to Jackknife where you like take a subsample?
The question is, how is this related to Jackknife? I'm going to rephrase that as, how is this related to Jackknife? Technically, this is a completely different thing than Jackknife, because this is asking questions in the space of the data, whereas Jackknife was asking questions in the space of the parameters, for which we don't know the truth. Here we do know, even if you're like frequentist or Bayesian, you believe that the data are there. So here so this is only in the space of the data. So in that sense, it's different from Jackknife. But you notice it has the same structure as Jackknife. It is exactly the same structure. And yes, you can leave out chunks of data if you want and predict chunks of data. And there's one additional thing is that cross-validation, remember Jackknife had to be comprehensive. We had to do m samples leaving out 1/m of the data. Cross-validation does not. In fact, sometimes cross-validation is just done as validation, where you, before you start, you mark a set of the data as your validation data, and you just fit in with the non-validation data and check on the validation data, and it's like, that's it. And that's also legit. There's all sorts of legitimate things you can do here. That cross-validation and validation is a whole framework of methods you can use to test accuracy of prediction and appropriateness of model. Yes?
If you maximize cross-validation likelihood, is there a way to estimate when you're still overfitting? If you just try so many different models that you fit, you basically like fit to the cross-validation.
Yeah, Miles is asking whether if you optimize the cross-validation likelihood, or cross-validation scalar or whatever, do you select good models and can use it for inference? And the answer is yes and yes. You can use it for inference. It does select good models.
But do you overfit to the data? Like if you show it, if you take your entire data set and you segment it.
You might be asking there's two questions you might be asking. He's asking about overfitting and cross-validation. One question you might be asking is, does it generically find a model that overfits? Generically, it does not. In fact, that's the whole point of cross-validation, is to avoid it. However, very, very principled machine learning people prefer a pre-assigned validation set to any cross-validation. Because it is true that when you're doing a cross-validation, you are looking at your whole data set when you do your fitting, whereas the truly principled thing to do is to pull off a validation set before you start and never look at it. You give it to your office mate and they only let you see it when you're done. So that is a better thing to do. And that's related to this problems in cosmology around blinding and problems in statistics around reproducibility and failure to reproduce and so on. So the short optimistic astrophysics answer is this prevents you from overfitting. And the long statistician principled like reproducibility crisis answer is you're not allowed to even do this. You have to trim off some of your data, sequester it in a vault, build all of your hypotheses on your hypothesis generating part of your data, and test all your hypotheses on the data in the vault. That is a possible subject for a future. We could put, if people want blinding, we could put blinding and all those kinds of reproducibility into a future class. Caitlin.
So I just want to ask, one use case that I'm aware of for using the Bayesian evidence is like, let's say you have some data, you don't know what the right model is, so you use the Bayesian evidence to tell you, okay, do I need a fourth order polynomial or a fifth order polynomial?
Yeah.
And like, let's say the Bayesian evidence says, okay, like both are like sort of fine.
Yeah.
So one use case that I'm aware of is that you can then use like what the Bayesian evidence tells you to sort of do something non-committal, where you don't have to commit to one model or the other. Is there a similar prescription for doing this with cross?
Caitlin is asking a very deep question. So one of the great things about the Bayesian evidence is it gives you a way to continuously weight a set of different models and use them all together. In fact, that's the whole point of Bayesian, right, is that nothing gets a certainty. You always have probabilistic, interpretable plausibility, which has the properties of a probability that you can use to weight things. So does cross-validation produce that? Technically, no. Cross-validation does not give you the weights. However, the cross-validation likelihood computed correctly here does have a probabilistic interpretation. So it is an interesting question, and it's possibly a research question, whether that could be used to weight models and whether that has good properties. That may be known out in the real world. I don't know the answer to that. That's the second thing you've said where I'm just like, I don't know. That's an interesting question. The fact that the cross-validation looks so like the Bayesian evidence, if you write it down a certain way, suggests that maybe there is a way to do that. And it would be frequentist safe, which would be sick. And I mean that in the good way. As you all know, I'm a Bayesian when I need to be, but sometimes if you can avoid it, it helps you. Good. Questions? Okay, let me say one last thing before I let you go. I only have a few seconds anyway. Okay, now, remember the last thing we were going to consider is the possibility that you might just model your noise. And there's exactly one thing I want to say. So remember on the first day, I redefined chi-squared. Well, I didn't redefine chi-squared. I rewrote chi-squared in a beautiful geometric way. And my rewriting of chi-squared is data minus model, which in our case was like MW, or I'll call it M theta to be consistent with our parameters now, transpose C inverse y minus M theta. Now, that's how I wrote chi-squared on the first day. And I pointed out things like this is a metric distance between your data and your model and so on. And then I also pointed out that you don't actually have to do this. You could be doing g of x given parameters. And it could be nonlinear. Everything I'm going to say right now works for nonlinear models as well. So you have some chi-squared, which I want to write in this geometric way. Now, all of my beliefs about the noise in my data come in here. And this thing, this chi-squared, is sort of like the log likelihood if the likelihood is Gaussian. Okay? But if I really write down the log of a Gaussian, it's not quite this. So let me just write it. So let me just rewrite it, not as chi-squared now. Now I'm going to say the log of the likelihood. And that's -1/2, because remember we minimize chi-squared and we maximize the likelihood. So there's a -1/2 there. And now what I'm doing is I'm taking the log of a Gaussian, or really a product of Gaussians, but it's one big-ass Gaussian. So the log of the likelihood is -1/2. This is the quadratic term, e to the minus x minus mean squared over sigma squared. There's the quadratic term in the Gaussian. But that's not the only term. There's also a normalization out front, which looks like, I'm good. I'm going to write it like this. -1/2 ln C inverse. I'm writing it as C inverse because, you know, I love inverse variance tensors and I hate variance tensors. I'm writing it as C inverse, but you could write it as +1/2 ln C if you want. And then there's some 2 pi's. Oh, and this, you can't take the log of a matrix. This has to be a determinant. And if you really want to get technical, there's a 2 pi in there, which, you know, little unpleasant. But I'm going to drop the 2 pi, even though it is there and I care about it a lot. The determinant of C inverse. And then there's some constant factors, which are about 2 pi's in the number of dimensions. You can actually put your 2 pi into here. Anyway, I'm not going to deal with that. So now, imagine, now we were just dealing with this thing. Why were we just dealing with this thing and ignoring this thing when we were working before in chi-squared? It's because we were only working on this term. We were only working on our prediction for the data, the mean prediction for the data, the mean prediction for the data. Imagine now we're going to start messing with our noise model and believe with our noise model parameters. Then we're going to be changing this object. If we're changing that object, then we're also changing this object. So there's exactly one fact I want to get across, which is that if you start messing with your noise, you cannot just do chi-squared. You have to do chi-squared plus a determinant of a matrix. if you don't do that, what you'll find is if you just use chi-squared, one of the ways to minimize chi-squared is to blow your errors up to infinity. Then your inverse variance goes to 0, and you get 0 for chi-squared, which is very convenient. But this term saves you from that. And sometimes people even refer to this as like a regularization of chi-squared, but that is not correct. This is really the log of the likelihood. The log of the likelihood has a quadratic term in it and a determinant term. One way to think of it is, this is the exponential part of the Gaussian. This is the normalization out front. And the reason it has a determinant in it is the normalization is about the area of the ellipse, or the volume of the ellipsoid. And the determinant of the tensor is the volume of the ellipsoid. So this also still has a beautiful geometric interpretation. And this is something that comes into Bayesian evidence and things like that as well. And this is kind of your hint that things are getting scary if you start modifying the noise. If you start modifying the noise, you start carrying around determinants. And determinants are notoriously very hard to compute, and notoriously related to the Bayesian evidence, which is also very hard to compute. And in fact, when you talk to linear algebra people and you say, I need to compute this, many linear algebra people will say, no, you don't. You only need to compute that. And I'm like, no, I actually need to compute this as well. And then you argue with them for about an hour, and then at the end of it, they're like, oh, you need to get the determinant, and then they leave. Because there's nothing fast. There's all sorts of fast methods for structured matrices and stuff here. There's nothing here. There's almost no research on fast computation of determinants. There's actually a couple of people at Courant who work on it, and there's people at CCM who have some ideas, but really all of the research has gone into this, and no research has gone into that. And that means that if you get into this noise modeling and you want to now start doing some kind of Bayesian inference where you're also modifying the noise, you are going to have to carry around these terms, and they will kill you. And we will talk about that when we get to Gaussian processes, which is another thing. So Gaussian processes is a place where we naturally modify noise. We'll be doing Gaussian processes later in the spring. And we will face the determinant in Gaussian processes, and we will cry. Okay, we're done. Class dismissed.
Only 1 minute.